everybody. My name is Tom Steffen with Gould Water Technology, and today we're going to talk about motor mysteries, all things practical with both submersible and surface mount motors. So we're going to talk about nameplate data, installation, cooling, grounding, surge protection, and troubleshooting at the end. Some of the material that was used for this presentation is on the screen. The first is what we call our MAID manual, and that stands for Motor Application and Installation Data. The one on the right is also a document of ours, and that's the service manual. And that's a little pocket service manual with a spiral binder on it. That's good for carrying with you, keeping in the truck. The two in the middle are some additional resources that you might find handy. The first one here is Electrical Engineering Pocket Handbook by ESA, and Ugley's Electric Motors and Controls book. So both of those are very good reference materials. So all of these are reference materials. They are not designed to per se memorize, any piece of information in there, but you want to keep these documents handy so you can refer to those in the field. So, today we're going to talk about really AC induction motors, but let's talk a little bit about the difference between an AC induction motor and a permanent magnet motor. The reason why I think it's good to just talk a little bit about this today is because we are seeing more permanent magnet motors in the marketplace today, whether it be submersible or surface mount motor. So let's talk a little bit about, what is the difference? So we can see here permanent magnet motors are structurally very similar to a AC induction motor, except that the rotor is comprised of a solid permanent magnet instead of a hollow cylinder with conducting bars. So we can see here in the picture here, the rotor for the magnet, a solid permanent magnet, as opposed to the induction motor, which is a hollow cylinder with conducting bars. So again, today we're going to really focus on the induction motor, but I think it is important to understand the basic differences between the AC induction motor and the permanent magnet motor. So here's some things to think about in terms of the differences here on the bottom. Again, ACIM, AC induction motor. The one big difference is that is an asynchronous motor. There is what we call slip in that motor. And basically that is where the motor does not run at the same rotational speed as the rotating magnetic field. Whereas the permanent magnet motor, that's a synchronous motor. And synchronous is the motor does run at the same rotational speed as the rotating magnet. So that's one key difference. Another key difference here is, do I need a VFD? So as most of you know, we don't need a VFD with the induction motor. However, we certainly can put one on that motor. With a permanent magnet motor, we have to have a VFD with that motor. So that's one key difference. And so there are some differences here as well. Let's just focus on one, and that's efficiency. The one key difference with that permanent magnet motor is also that it's very, very efficient compared to the induction motor. And frankly, that's why we're seeing more and more of these motors in the marketplace today. And I think we'll see more in the future as well. So let's get back to the induction motors. Let's start with the submersible pump nameplate. So as we can see here, we have an MO5412, that's the model or the part number. and that's motor. 05 is half horsepower, 4 is 4-inch, 1 is a 3-wire motor with a ground, and the 2 is a 230-volt motor. Moving across here, we can see that's a half horsepower, 60 hertz motor, 230 volt. Amperage here is 5.5 amps. So sometimes we see FLA or full load amps. In this case here, we're just showing amps. So basically they're the same, full load amps, amps. Service factor. We can see this motor has a service factor of 1.6. Well, what does that mean? Service factor is just what it says. It's a factor. So we could, if we wanted to, multiply the service factor of 1.6 times the nameplate horsepower. 1.6 times 0.5 is, technically we have a 0.8 horsepower motor. The important thing, I'd say the practical thing for, the installer is because this motor has a service factor, and if we are in the service factor, which is from 0.5 to 0.8, right, in this case, we can see that we are going to be indicating, showing max service factor amps. And so we can see here that the max service factor amps is 6.3. The bottom line is that when we're measuring amperage out in the field, or we are setting the proper amperage for a VFD, for this type of product, we want to base all those on the service factor max amps. In this case, it's 6.3. Okay, so now it gets a little bit more complicated here when we talk about a surface mount motor. So here is just an example of a Beldor nameplate. There's an awful lot of stuff on here. We're gonna just cover a few of these, I would say most commonly confused values. So, we'll see, you can see here the catalog number, the specification number, horsepower 7.5 in this case. And now we get into an area where there's always lots of question and confusion. So this particular motor, in terms of voltage, is a tri-volt motor. So we can see here 208-230/460. And so because there's a dash and a slash, that often leads to confusion. With this motor, this is a true tri-volt motor. So this motor can be operated with an input voltage of 208 or 230 or 460. Now the amperage here, you can see corresponds to the voltage. So again, it's not service factor amps, right? It's just amperage. And it just corresponds to voltage. So if you are operating at 230 input and we've wired it properly, right? In this case to low voltage, the amperage is 17.4. RPM, 3450. The frame size has to do with the size of the motor. We can see it's a 60 hertz motor, and it is a 3-phase motor. So next we come into service factor. Just like the submersible pump that we looked at, this does have a service factor of 1.15. So we should see a service factor amperage value, or put another way, there are service factor amps, right? Because if you have a service factor, you have service factor amps if you're into the service factor. But we can see with this motor nameplate, service factor amps is nowhere to be found. Well, why is that? Well, we can see here that service factor greater than 1.15, which we don't have in this case, right? It's just 1.15. you don't have to list it, right? But if it's greater than 1.15, you must list the service factor amps. So I think it's an example here where just because the motor does not show service factor amps does not mean that they're they're not there, right? The other important thing here, there's lots of other stuff. Look at this, usable at 208. That kind of confirms that we can use this at 208 supply voltage. You've got some bearing information. DE is the drive end bearing. ODE is the opposite drive end bearing, gives you some bearing information. It's a TEFC motor, totally enclosed fan cooled, and serial number. So serial number is a unique number, but oftentimes that's where your date code is buried, right? So we need to know, how to read that, because all motor manufacturers use a different system. And we can tell you that Baldor uses this system here. So we can see that the 1-3, the 13 is the year, the 02 is the month, and then the 01 is the day. So that's how you decipher date code, at least with a Baldor motor. Okay, the other thing that you will see on a motor like this is the wiring diagram, right? So we can see here we've got low voltage and we've got high voltage. So with this type of motor, you're going to open up the conduit box and there's going to be 9 wires sticking out. They are going to be numbered, right? But the installer has to wire that up based on whether they want low voltage or they want high voltage. So if you remember our scenario from the nameplate, low is 208 or 230 and high was 460, right? So everything to the left of the slash is low and to the right of the slash is high. So let's just say in our case, we are going to bring 230 volt into this motor. So therefore we want to wire it up for 230 or for low in this case. So we're going to look at the diagram for low, and we can see here, if you've never done this before, it can be a little confusing. We can see that numbers 4, 5, and 6 are tied together. Then we take 3 and 9, put those together, 2 and 8 together, 1 and 7 together, but we don't put a wire nut on yet because we're going to bring our power supply in to this area. So line 1, line 2, line 3 doesn't really matter, right? Because it's 3-phase. Just going to bring in 1 line here, 2nd line here, and then the 3rd line here. So now you're going to wire nut those together. So wherever there's a wire nut, you should have 3 wires, right, for low. We'll just take a quick peek at high. And again, in this case, that would be 460, right? So we take 6 and 9, put those together, wire nut those off, 5 and 8, put those together, 4 and 7, put those together. So then we take 1, 2, and 3, connect those to your 3 different legs, right? And so in other words, for high, if I look at a wire nut, I should see no more, no less than 2 wires for each wire nut. The other piece of information we can see here is interchange any 2 line wires to reverse rotation. So this is 3-phase. So 3-phase can and will run backwards. And certainly we're talking about that connected to a pump, and the pump will actually give you some flow and some pressure, even if it's running backwards. So there's a little tip here saying interchange any 2 line wires for reverse rotation. Now what's different there with a drive is if you do have a drive or a VFD, you want to change any 2 leads on the output of the drive. Okay, so let's talk a little bit more about rotation. in terms of our installation process. So here's a drive. We can see the input is titled mains. The output is titled motor. And here is where we would change the rotation if we have a drive. So we're going to go to the output of the drive, reverse any two of the three leads. And that is going to change the rotation. So that's how to change the rotation. And here we've got a couple examples of some surface mount. Surface mount's a little bit easier, right? Because we can actually see something turn. In this case, I'm looking at the back of a surface mount motor. I've taken off the dust cover and I can see the shaft rotation. So I could just bump it and visually see what direction that's going. Most motors will have an arrow to indicate rotation, and most of the time, always want to follow the arrow, but most of the time it's counterclockwise viewing from the motor end. On the right, we have an ESV. So an ESV is a multi-stage, normally vertical orientation, multi-stage, usually for a booster application. So in this case, I've got two arrows to look at. I've got one arrow on the pump body. And if I take the coupling cover off, and again, we're just going to bump it just to check for rotation. We can see that that coupling also has an arrow on it. We can see the rotation. So we can check rotation there. Now with a submersible, it's not quite as easy, right? It's because we probably are not going to pull the pump in to check the rotation right at the coupling, right? So, but for a submersible, we know that the most flow and head are the correct rotation. So you might have to do a comparison with the two different directions, right? So we are talking about three-phase here, and normally at startup, right? And so we always want to check the rotation at startup. And again, we're going to change any two leads on the output if we have a drive. Okay, installation. So there's an awful lot of stuff to talk about with submersible motors. And let's just hit a couple of these things here. Certainly grounding is required, right, by the MEC, also for safety purposes. This is a good reminder here saying that all three-phase pumps need overload protection, whether that's in your control box or your VFD, because they don't have built-in overload protection, you know, like some of your smaller single-phase motors. The next bullet here really just talks about cooling. And anytime you look at an installation manual with a motor, that motor manufacturer is going to have some specs regarding, you know, the number of starts or something related to cooling, because cooling is a big issue with motors, right? So when you start a motor in, let's say, a fixed speed application, you give it a lot of amperage, right? And amperage is heat. So now you have to dissipate that heat somehow. So that's always a concern from the motor manufacturers. The next one here, pumps greater than or equal to 2 horse installed in large tank should be installed with a flow inducer sleeve. So I have a picture of that, so we'll cover that. And that just has to do with knowing that a submersible motor is cooled by water going past the motor. And that's what you normally get, right? If we have, for example, a 4-inch pump in a 5 or 6 inch well, for an example, that's a bottom feeding well that comes up past the motor and cools it. So that's probably what we would consider more of a normal type application. But if you put that pump in a large tank, for example, maybe it's a 2-pump system in a low yield well, then we have to make sure that that water flows past the motor in order to cool it properly. Okay, so let's talk a little bit about wire sizing. And here we have two examples. So the top chart is just an example of single phase. And we're just looking at 3-wire here as an example. But single phase is on the top chart. And then 3-phase is on the bottom chart. And really just to compare in contrast. So, one thing we need to know the voltage, we need to know the horsepower. If we have the model number, we have all that information. And, manufacturers are all a little bit different. So it's a good idea to use the particular manufacturer's wire sizing charts because the amperage does tend to vary a little bit. So once we know either the model number or, again, phase, voltage, and horsepower, then we can look at our charts. And for an example, in this case, a half 230, again, single phase 3-wire, this indicates that we can run 348 feet. So let's compare that a little bit to 3-phase. So same chart, right, in terms of the way it's laid out, but we're looking at a 3-phase motor now. And let's do the same comparison, half 230 3-phase, 14-wire 756. So, the bottom line there is with 3-phase, I can use smaller wire, like in this case here, right? And so why is that? Well, it's all about amperage, right? So compare the amperage of the 3-phase motor, and let's look at service factor amps. The half 230 3-phase is 2.9 versus 6.3 for the single phase. So that's why, those wire charts are different. And that's, one of the big advantages that we have with drive. Most drives require 3-phase motor, right? Okay. Speaking of drives, so the one other tip here, let's talk about with wire sizing if you have a VFD system. And the bottom line is for that, I would say, is that use the wire charts that come with the product itself, and they should be in the installation manual. The reason is, for an example here, we can look at the Solo 2, and we've got all models service entrance to controller. So that's what I call the input, right? So service entrance to controller, there's a chart for that. And then there's another chart, what I would call the output or controller to motor. So there's two charts that we need to pay attention to when sizing the wire for a drive. Okay, so let's get back to cooling a little bit. Again, most of your motor manufacturers will give you some sort of chart in terms of, maximum starts per hour. And this is just one example here, and we'll give you some limits. It's based on horsepower. And then we can see here single phase versus 3-phase, and this is starts per 24 hours. So normally that's not much of an issue, but it's a good thing to pay attention to. And again, what is the issue with that? Because when you start a motor, certainly fixed speed, you give it startup amps, and which are high amps, and then high amps means high heat. So that's really the concern here. And notice that this number, this starts per 24 hour, goes down as the horsepower gets bigger, right? Because you have more amperage. Let's look here at a picture of the flow sleeve that we talked about just a minute ago. And so what we're seeing here is that if you do put a submersible pump in a large body, like a tank or something like that, it's two things to think about. One is the flow sleeve that redirects the water past the motor for proper cooling. And the other thing is, due to the thrust bearing, we want to tip that up 15 degrees from horizontal to put some thrust on that bearing. The other thing that has to do with cooling, in our typical res water systems is the tank. So we can see here the general rule of thumb for sizing our tank. And the general rule of thumb, and this is minimum, by the way, this is not, I would say even recommended would be double this, but minimum would be a 1 minute minimum run cycle time for pumps and motors up to 1.5 horses and 2 minutes for 2 horse and larger. So that's a pretty standard rule of thumb. Again, that's minimum. Recommended would be double that. And basically it's saying that, the drawdown, if you match the drawdown of the tank to the capacity of the pump, then let's say a 10 gallon per minute drawdown to a 10 gallon per minute pump that's pumping 10 gallons per minute, then we have our 1 minute runtime. So certainly the tank size has a lot to do with the proper cooling of our submersible motor. Okay, grounding. Grounding certainly is a requirement by the NEC. And just a little bit here on grounding. One electrical supply line is generally connected to earth to eliminate hazardous voltage, so it's a safety issue. The failure of insulation on any item of equipment. So, what we're talking about here is the insulation, insulation of the windings has gone bad, right? If that happens, it can subject the user to dangerous shock because one of the electrical lines is then unintentionally connected to the equipment, enclosure, or housing. So that's a shock hazard. When this happens, a voltage equal to the line voltage, right, can appear between the enclosure and the ground. And so protection is the enclosure must be grounded, right? And so it wasn't all that long ago, right, that there was a change to your 2-wire submersibles are 2-wire with the ground, and your 3-wire is 3-wire with the ground, but we still call it 2-wire and 3-wire, right? Okay, so this is a requirement, and it's pretty clear in terms of the NEC, the National Electrical Code, motor operated water pumps, including submersible pipe, metal well casings where a submersible pump is used in metal well casing shall be bonded to the pump circuit equipment ground and conductor. So shall be means must, right? So that is a requirement. So a lot of questions come up regarding, surge arresters or lightning arresters. And so let's spend a couple minutes talking about that. If we look at a standard, 4-inch submersible pump here on the left, and we look at some components here on the right, the first thing that we see here is the top end bell on the bottom side, which we don't normally see because, these are not repairable. But if you were to take that top end bell off, and you would see these surge arresters. Now it's a little tough to see in the picture, but we can see that there's one surge arrestor for every leg, right? So in this case, we know that's a 3-wire motor because I have 3 surge arresters. If you have a 2-wire motor, then you're going to have 2 of these little guys. So, this type of motor does have some built-in surge protection. A lot of people ask, can I add surge protection? And, in some cases it's necessary because of the presence of lightning in surges. And so, yeah, certainly you can. Normally though, if, no matter what you have, if there's a direct strike, you might still have some issues. But here's a couple examples of some additional surge arresters. The one on the right is fairly new for us, and the one nice thing about that is it's got a light right there and indicates that if it's on, it's working, and if the light is off, you know, there's an issue, maybe it got hit and took it out, and so we need to replace that. So one of the big questions that we get is, okay, surge arrestor on my VFD, on my drive. You know, can I put it on the input or could I put it on the output? That's a fairly common question. And if I can, then how do I size it? You know, which one do I need? So, you know, here is some information that we created looking at the VFD. And you can skip all the stuff in the middle, and basically says that if you need a surge protection for any of these, for example, here's a couple examples of the particular part numbers to use. The one thing that's a little different about VFDs is the output voltage varies, and that's normal, right? And because that output voltage varies, it's difficult to pick the right one, to size the right one. So from our standpoint, we don't have a recommendation on the output, but certainly this is an example of a selection for the input side. Okay, let's talk a little bit about troubleshooting. And, you know, we often talk about the VARI or very easy methodology, and that's voltage, amperage, resistance, and insulation. So let's start a little bit talking about voltage. You know, normally your voltage tolerance on any piece of equipment is normally 10% of the nameplate. Well, some drives are actually different. So if you look at the Solo 2, that tolerance is a little bit broader than that, and it's 196 to 265. So some VFDs have a little bit more of a tolerance window. So low voltage, you know, so the reason why we're checking that, obviously, you know, do we have voltage? Do we have the proper voltage? Is it high? Is it low? You know, because low voltage and high voltage can lead to high amps, right? So if we're getting high amps, maybe it's tripping or something like that, we should go check the voltage. If possible, now, if the pump is not running, this is not possible, but if possible, test under a load. That just means that the pump is running. And for example, like 230, we're going to test line to line and line to ground. Line to ground is going to be half that of line to line in the 230 system. And also just note that on a drive, the output does vary. So if you go to measure the output voltage and it is running, you are going to see that change. But you can measure that. It's recommended if you do measure that to have this type of meter here that has a low pass filter, that little guy right there. Okay, amperage. And, you know, a couple quick things about amperage. One is, you know, we're talking about the output side, right? And so, and one line at a time. So we often see that certainly for, you know, people just starting out, we want to, you know, grabbing all the wires. So we want to have the output in one line at a time, as we can see here. And we got a current clamp, right? So, and power's on, so we have to use caution. And so we're going to get an amperage reading. Now, for the pumps that really we're talking about today, you know, the smaller, lower horsepower submersibles, we do know that they often run in service factor. So we need to be looking at the service factor amps as opposed to the full load amps in determining if it's high or not, right? Okay, here's amperage. So, you know, you can look at the control. Let's say it's a 3-wire. You can look at the control box that has some information on there. We should probably be a little bit cautious about that because, you know, maybe that control box was added later and it doesn't quite match up to the original motor that was installed. So it's always good to look that up. And let's just take a quick look here at your 2-wire single phase motors and pick on the half 230 again. We can see 4.7 service factor amps. Okay, so we measure amperage and we get high amperage or we get low amperage, right? So if you do get high amperage, you know, what could that mean? You know, it takes us, you know, one step closer, but it could be that our input voltage is off, not within that tolerance window. On the impeller side, you know, maybe that impeller is dragging. Maybe there's some rub, and that's going to create some higher amperage. Maybe the motor itself is starting to go bad. The insulation of the motor is starting to break down. The last one is duty point, and duty point just means that, well, maybe we're operating to the right of the curve, right? High flows. And with a centrifugal pump, high flows, you're going to see higher amperage with your higher flows compared to the amperage measured at lower flows. So maybe it's, you know, something has changed in the system and, you know, the TDH or total dynamic head has been reduced. You know, pumping levels change and all that. And we're operating maybe farther to the right than we were in the past. Okay, so VAR. So R is your line to line. So I personally try to keep this straight by line to line versus line to ground. So winding resistance is, we can see here in the picture, we're measuring line to line. So this is something that needs to be looked up, you know, in the main manual or the service manual, and there is a spec. For example, here, my spec is from 2 to 2.6 ohms. And so we can see here the example is I've got the motor on my test bench and certainly no power, right? So I'm measuring ohms with my meter and I get 2.4 between the yellow and the black. So I looked that up in those books and the spec says you should be getting between 2 and 2.6. Well, tricky thing about these meters, there is some resistance in the wires, which is about 0.2, not a huge deal. But if I subtracted that, I'm 2.2, so I'm right within the specification of that motor. So the nice thing about that book is that it tells you exactly if it's low, tells you what that means. If it's high, it tells you what that means. Let's take a quick look here. You know, what is the difference between your winding resistance of a single phase motor versus 3-phase? So, you know, with a single phase motor, we can see the range, right? And we can see that, we use this for an example, half 230 again. You got 3 wires, right? So you got the black and yellow is 5-1 to 6-1. The red and yellow, otherwise called start, is 12-4 to 13-7, right? So that's where you would look those values up. And just for the heck of it, let's take a look at 3-phase, and because sometimes there's some confusion there. So if you do have a 3-phase motor, it just, I mean, this happens to be this little slice here. But once you look up your motor, you're going to see this, there's only one set of values, right? A min and a max, but you got 3 leads on your 3-phase motor. It basically says that they should all be the same, right? And so that's what that's saying. All right. So 3 leads, they're all the same. 1 to 2, 2 to 3, 1 to 3. Okay, so in that book, your winding resistance tells you what that means. That's the great thing about that book. If you do this test and those numbers are less than the spec, then you've got a short, right? So there's something shorted in the motor. Number three, if it's greater, right? So you come up with a value that's greater than the spec, you've got an open, right? So again, if we're measuring this at our bench, then we're really just looking at the windings of the motor itself, right? We're not really looking at any other wire. And here's where that comes a little tricky, because if you, let's say you want to do this test at the wellhead or, at the control box or something, turn the power off and disconnect and get into the leads. You can do this, but you're using an ohm meter. So that ohm meter is measuring the resistance of all that wire, right? All the way down to the pump. So you have to account for that. And in that book gives you a little chart that says, okay, cable size, and this is resistance per foot. That, again, if you know what size wire and how many feet, you do the math here, and then you would add that, to your spec, let's say. So this gets a little trickier, when you're doing this at the wellhead or at the control box or drive. Okay, so the last one here is what we call the I, or the insulation resistance, and that is line to ground, right? So let's take a look at the old venerable Simpson 372, and we can see that, so the manual is going to take you right through it, that service manual. Set the dial to R times 100K, 100,000, and check we're going hot to ground, right? And no power, disconnect, no power, and hot to ground. So with this meter, we got to do some math, because we can see, which you probably can't see, but this has pegged the meter, and it's a brand new motor. It's pegging the meter, and the number here is 500, right? So remember, we set the scale to R times 100K. So you got to multiply that by 100,000, and you come up with 50 million ohms, or 50 meg ohms. All right, so great meter. And this meter puts out 50 volts, right? That's the max. So again, what does that mean? Well, it indicates it's a brand new motor. There's nothing wrong with it. I don't have any connection between the hot leads and the ground, right? So let's take another look. If I do that same exact test using a Fluke 1587, which is what we happen to use at the schools, and I'm just going to use the ohm meter, all right? Well, I do the same test. I got the same motor, and I get an OL. Well, OL means that it's an open lead. You have no connection, no continuity between the hot leads and the ground. Again, it's showing that that's good, that there's no issue, right? But it's a little different. The real beauty of those meters is, we'll see that in a second here. So in that spiral bound book, again, it's going to give you a chart, and chart either ohms or meg ohms, and it's saying 20 meg or greater, right? It's a new motor, all the way down to less than 0.5 meg or 500,000. We got a problem. We've got to pull it and see what's going on. So it's a nice little chart that's provided, but keep in mind that is based on the Simpson 372, which puts out 50 volts. Okay. So what happens if you want to use your brand new, in this case, Fluke 1587 insulation multimeter, does everything for you? We got to think about what voltage we want to use. See here, it says 500 volts. Well, if we look at number one, determine the test voltage. What voltage do you want to send through the windings, pressurize the windings to see if it's grounded, right? So the book that we looked at earlier from ESA says if your voltage, your winding voltage, the voltage of your motor is less than 1,000 volts, test it with 500. Well, that makes it easy for us because these meters default to 500 and I don't need to change it, right? Perfect. I don't need to adjust that. I leave it at 500. I do my test. So we're going to test each lead to ground. Right, again, this is no power, the power is off, and they're disconnected, right? So in this case, again, I've got it back to the workbench. I'm just looking at that motor itself, and I got to test each hot lead to ground. So in this case, I've got a 3-wire, so I've got a black, a yellow, and a red. So this is just showing one. And I'm set to send 500 volts. I press, hold, and release. And now I get 550 megohms, 550 million ohms, right? Well, one thing that we know is that this meter is pegged, it's maxed out, which is good, right? With this sort of test, you have no internal connection. Your windings are in good shape. They're not grounded inside the motor. The problem comes with the scale, right? So if we like that old scale, which is the one we just showed here. It's based on the Simpson, which is putting out 50 volts, right? And it kind of gives us some good stuff in between, right? Normally what you're going to see is perfectly fine, you know, very high value, or it's maybe a dead short. Occasionally you'll get into some of these values in between. Well, if you like this chart, what you could do, and if you have this meter, all I got to do is put it to 50, right? And so you adjust that test voltage down to 50, do the same test, kind of a black background here, so it's hard to see, but you got your leads and your ground, right? And notice how that changes. Now I'm getting 55 megohms versus a 372 is 50, right? So we're a heck of a lot closer to that previous scale that we had in the book because we're using 50, which is, you know, what the Simpson 372 is based on. So you can always go down to 50, and you know, if you're very familiar and if you like that chart, you can use 50. Okay, I hope that helps. Again, that's you know, a little bit on submersible motors and some surface mount motors. Really, most of the common things that that we deal with, you know, on a daily basis, and things that often you know, lead to confusion and people have questions on. So, thanks a lot for watching.